Hello everyone, let's discuss bifurcations of 1D flows. First, let's discuss the general idea of bifurcations. Although the dynamics of 1D systems are quite limited, because all systems either settle down to an equilibrium point or diverge to plus minus infinity, they can have interesting dependence on parameters. The word bifurcation refers to sudden change in the qualitative structure of the flow, i.e. equilibrium points being created or destroyed, or their stability changing, when one of the parameters of the system is varied. The parameter values at which these qualitative changes of the dynamics occur are called bifurcation points. Now, let's discuss saddle node bifurcations. This is the basic mechanisms by which equilibrium points are created or destroyed. The typical example of the saddle node bifurcation is x dot is equal to r plus x squared. There are two equilibria if r is less than 0, at x star is equal to plus minus the square root of minus r. The positive equilibrium point x star is equal to the square root of minus r is unstable, while x star is equal to minus the square root of minus r is stable. There are no equilibrium points for r greater than 0. Now let's discuss transcritical bifurcations. This is a mechanism by which equilibrium points change stability as some parameter is varied. Consider the differential equation x dot is equal to rx minus x squared. The equilibrium points are the solutions of rx star minus x star squared is equal to 0, or x star is equal to 0 and x star is equal to r. It is easy to show that if r is less than 0, the origin x star is equal to 0 is stable and x star is equal to r is unstable. If r is greater than 0, then x star equal to 0 is unstable and x star equal to r is stable. Thus, there is an exchange of stabilities between the two equilibrium points as r increases through its critical value of r equal to 0. Then let's talk about pitchfork bifurcations. This bifurcation is common in physical systems that have some sort of symmetry. The equilibrium points appear and disappear in symmetrical pairs. There are two types, either supercritical pitchfork bifurcations or subcritical pitchfork bifurcations. For supercritical pitchfork bifurcation, the typical example is x dot is equal to rx minus x cubed. This equation is invariant under the transformation of x goes to minus x. The equilibria are x star is equal to 0 for r less than 0 and x star is equal to 0 or x star is equal to plus minus r for r greater than 0. It is called supercritical because the additional equilibrium points are found when the parameter is above the critical value, which in this case is 0. If we consider the equation x dot is equal to rx plus x cubed, we obtain the subcritical pitchfork bifurcation. Following on, let's mention hysteresis. Consider the dynamical system x dot is equal to r plus x minus x cubed. For r equal to 0, the equation has three equilibria, one unstable and two stable. The flow continues to have the same qualitative structure for r between minus r1 and positive r1, where r1 is equal to 2 over 3 times the square root of 3, which is the local maximum of x minus x cubed, and minus r1 is the local minimum value. For r equal to minus r1 or r equal to positive r1, the dynamical system is at a bifurcation point. For r less than minus r1 and r greater than positive r1, the equation has only one equilibrium point, which is stable. Next, let's discuss cusps. We consider the dynamical system x dot is equal to h plus rx minus x cubed. If we fix h equal to 0 and let r vary, we obtain the supercritical pitchfork bifurcation, and if we fix r equal to 1 and let h vary, we find the hysteresis bifurcation. We are interested to find what are the non-hyperbolic equilibrium points, as there the bifurcations occur. So we need f of x star equal to 0 and f dash of x star equal to 0, where f of x is equal to h plus rx minus x cubed. Solving these equations for h and r, we obtain the curve h is equal to plus minus hc of r, which is equal to plus minus 2r over 3 times the square root of r over 3. We get a cusp catastrophe surface. The term catastrophe is motivated by the fact that as the parameters change, the state of the system can be carried over the edge of the upper surface, after which it drops discontinuously to the lower surface. And, as ever, thank you for watching.